Hello friends and welcome. In today's deliberation, we shall discuss the third lecture of the topic Ionic equilibrium. These are the important points that we are going to highlight. First, we shall talk about buffer solutions and their composition. Then we will be talking about the mechanism of buffer action, followed by the applications of buffers. And finally, we shall discuss solubility product, and their applications. To begin with, let's talk about buffer solutions first. A buffer solution is one which resists change in pH when small quantities of an acid or an alkali are added to it. There are two main types of buffer solutions, and these are acidic buffer solutions and basic buffer solutions. An acidic buffer solution is simply one which has a pH less than 7. Acidic buffer solutions are commonly made from a weak acid and one of its salts, that's often a sodium salt. A common example would be a mixture of ethanoic acid and sodium ethanoate in solution. In this case, if the solution contains equal molar concentrations of both the acid and the salt, it will have a pH of 4.76, that is acidic pH. We can change the pH of the buffer solution by changing the ratio of acid to salt or by choosing a different acid and one of its salts. Then, alkaline buffer solutions. An alkaline buffer solution has a pH greater than 7. Alkaline buffer solutions are commonly made from a weak base and one of its salts. A frequently used example is a mixture of ammonia solution and ammonium chloride solution. If these are mixed in equal molar proportions, the solution will have a pH of 9.25, that is basic pH. Now there's an important question. How do buffer solutions work? Or, what is the mechanism of action of buffer solutions? A buffer solution has to contain things which will remove any hydrogen ions or hydroxide ions that we might add to it. Otherwise, the pH will change. Acidic and alkaline buffer solutions achieve this in different ways. So dear friends, let's first discuss the mechanism of action of acidic buffer solutions. As a typical example, let us take a mixture of ethanoic acid and sodium ethanoate. Ethanoic acid is a weak acid and the position of this equilibrium will be well to the left. Symbolically, we can say CH3COOH aqueous, that is ethanoic acid, will be in equilibrium with its ions CH3CO negative aqueous, that is ethanoate ion, and H positive ion. Adding sodium ethanoate to this adds lot of extra ethanoate ions. According to Le principle, that will tip the position of the equilibrium even further to the left. The solution will therefore contain these important things. Lots of unionized ethanoic acid. Second, lots of ethanoate ions from the sodium ethanoate. And third, enough hydrogen ions to make the solution acidic. Other things like water and sodium ions which are present are unimportant to the argument. Now let us discuss what happens when we add an acid to this buffer solution. The buffer solutions must remove most of the new hydrogen ions that are added, otherwise the pH would drop markedly. Hydrogen ions combine with the ethanoate ions to make ethanoic acid. Although the reaction is reversible, since the ethanoic acid is a weak acid, most of the new hydrogen ions are removed in this way. Symbolically, we can show CH3CO negative aqueous, that is ethanoate ion, reacting with H positive aqueous ion to generate CH3COOH, that is ethanoic acid. Since most of the new hydrogen ions are removed, the pH won't change very much but will remain nearly constant. Now let us discuss what happens when an alkali is added to a buffer solution, how the pH remains constant. So Alkaline buffer solutions contain hydroxide ions and the buffer solution removes most of these. This time, the situation is a bit more complicated because there are two processes which can remove hydroxide ions. The first process is removal by reacting with ethanoic acid. The most likely acidic substance which a hydroxide ion is going to collide with is an ethanoic acid molecule. They will react to form ethanoate ions and water. Because most of the new hydroxide ions are removed, the pH doesn't increase very much. Symbolically, we can show that CH3COOH aqueous, that is ethanoic acid, reacts with hydroxide ions, that is OH negative aqueous, and it gives CH3CO negative, that is ethanoate ion, plus H2O liquid, that is water. So we see that water doesn't add to the pH of the solution and thus the pH remains constant. Now let's discuss the removal of the hydroxide ions by reacting with hydrogen ions. We should remember that there are some hydrogen ions present from the ionization of the ethanoic acid, as seen from the equilibrium. CH3COOH aqueous gives CH3CO negative, that is ethanoate ion, plus H positive aqueous. Hydroxide ions can combine with these to make water. As soon as it happens, the equilibrium tips to replace them. This keeps on happening until most of the hydroxide ions are removed and thus there is no pH change. Now let us discuss the applications of buffer solutions. Buffer solutions are one of the most important types of chemical reagents used in chemical research, biological research, and industry. Their usefulness stems mostly from their ability to resist changes in pH. Our body uses buffers to maintain a blood pH of 7.35 to 7.45, that is a basic pH, and also in a massive number of biochemical reactions involving enzymes. Enzymes are very complex compounds, often requiring precise pH levels in order to react properly, a role filled by organic buffers produced by our body. For this same reason, buffers are vital for a biologist or chemist performing experiments in the lab. A certain pH will often be required in order for the process being studied to occur, and buffer solutions are the only way to ensure these conditions. Buffer solutions are also widely used in industry. Industrial processes requiring buffer solutions include fermentation, dye processing, and manufacturing pharmaceuticals, etc. Solubility and solubility product. When a solute is added gradually in increasing amounts to a given amount of solvent at a particular temperature, a stage is reached when some of the solute remains undissolved, no matter how long we wait or how vigorously we stir. The solution is then said to be saturated. That is, a solution which remains in contact with undissolved solute is a saturated solution. At saturated stage, the quantity of the solute dissolved is always constant for the given amount of a particular solvent at a definite temperature. In case the solute is an electrolyte, its ionization occurs in solution and degree of dissociation depends on the concentration of dissolved electrolyte at a particular temperature. Thus, in a saturated solution of an electrolyte AB, two equilibria exist and can be represented as AB, that's a binary electrolyte, in its solid form is in equilibrium with its dissolved form AB. The dissolved form of AB is further in equilibrium with its ions, that is A positive and B negative. Thus, applying the law of mass action to the equilibrium, we have K, that is equilibrium constant, is equal to the multiplication of the concentrations of A positive ion and B negative ion divided by the concentration of the dissolved solute AB. Since the solution is saturated, the concentration of unionized molecules of the electrolyte is constant at a particular temperature. That is, concentration of AB is equal to K dash, which is a constant. Hence, the multiplication of concentrations of A positive and B negative is equal to K into the concentration of AB. Since the concentration of AB is constant, thus we can say the multiplication simply comes out to be K into K dash. Since both are constant, we have a new constant that's called Ks. Ks is termed as the solubility product and is defined as the product of the concentration of ions in a saturated solution of an electrolyte at a given temperature. Consider in general the electrolyte of the type AXBY, which is dissociated as AXBY is in equilibrium with X times AY positive plus Y times BX negative. If we apply the law of mass action to the equation, we get K is equal to concentration of AY positive into concentration of BX negative divided by the concentration of AXBY. When the solution is saturated, we have the concentration of AXBY is equal to a constant K dash. Thus, we can simply say that the concentration of AY plus raised to power X into the concentration of BX minus raised to power Y is equal to constant K into the concentration of AXBY, which is again equal to K dash. The multiplication of the two constants again gives another constant, that is Ks. The constant Ks is the solubility product. Thus, solubility product is also defined as the product of concentrations of the ions raised to a power equal to the number of times the ions occur in the equation representing the dissociation of the electrolyte at a given temperature when the solution is saturated. We should note that solubility product is not the ionic product under all conditions, but only when the solution is saturated. Now let us see what are the criteria of precipitation of any particular electrolyte. A very useful conclusion is derived from the solubility product concept. No precipitation of the electrolyte occurs if the ionic product is less than the solubility product, that is, the solution has not reached the saturation stage. There are three cases which we must understand well. So, case first, when ionic product, that's KIP, is less than the solubility product KSP, then solution is unsaturated in which more solute can be dissolved. Case second, when ionic product is exactly equal to the solubility product KSP, then solution is saturated in which no more solute can be dissolved. Case third is when ionic product is greater than solubility product. Numerically, KIP is greater than KSP. Then solution is supersaturated and precipitation takes place. When the ionic product exceeds the solubility product, the equilibrium shifts towards left-hand side. That is, upon increasing the concentration of undissociated molecules of the electrolyte, we have shift of the equilibrium towards the left. As the solvent can hold a fixed amount of electrolyte at a definite temperature, the excess of the electrolyte is thrown out from the solution as precipitate. Thus, for the precipitation of an electrolyte, it is necessary that the ionic product must exceed its solubility product. Dear friends, now let's discuss the applications of solubility product. There are various applications of solubility product, some of which are listed as purification of common salt, salting out of soap, manufacture of sodium bicarbonate, application of solubility product in quantitative analysis, fractional precipitation, stability constant, solubility of metal hydroxides in acidic medium. Now let us discuss one or two of these applications. The first one is the purification of common salt. Natural common salt consists of many insoluble and soluble impurities. Saturated solution of common salt is prepared and insoluble impurities are filtered off. Hydrogen chloride gas, that is HCl gas, is circulated through the saturated solution. Hydrochloric acid HCl and sodium chloride NaCl dissociate into their respective ions as NaCl gives Na positive plus Cl negative both in their aqueous forms. Similarly, HCl gets converted to H positive plus chloride ions Cl negative. The concentration of chloride ions increases considerably in solution due to ionization of HCl. Hence, the ionic product of sodium chloride, that is concentration of Na positive into concentration of Cl negative, exceeds the solubility product of sodium chloride, and therefore pure sodium chloride precipitates out from the solution. The second application is salting out of soap. Soap is a sodium salt of higher fatty acids. From the solution, soap is precipitated by addition of concentrated solution of sodium chloride. Soap and sodium chloride are present in the form of ions. Symbolically, we can show CnH2n plus 1 COONa, that is sodium salt of higher fatty acid, gives CnH2n plus 1 COO negative, that is carboxylate ion of higher fatty acid plus sodium ion Na positive ion. Similarly, NaCl, that is sodium chloride, dissociates into Na positive and Cl negative, that is sodium and chloride ions. Thus, the concentration of sodium positive ions increases considerably on addition of NaCl solution. Hence, the ionic product concentration of CnH2n plus 1 COO negative and Na positive ion exceeds the solubility product of soap. Therefore, soap precipitates out from the solution. It's important here to discuss the relationship between solubility and solubility product. Salts like silver iodide, barium sulfate, lead sulfate, lead iodide, etc. are ordinarily considered insoluble, but they do possess some solubility. They are sparingly soluble electrolytes. A saturated solution of sparingly soluble electrolytes contains a very small amount of the dissolved electrolyte. It is assumed that whole of the dissolved electrolyte is present in the form of ions, that is, they are completely dissociated. The equilibrium for a saturated solution of any sparingly soluble salt may be discussed as AXBY gives X times AY positive plus Y times BX negative. Thus, solubility product Ks is equal to the concentrations of AY positive raised to power X and Bx negative raised to power Y. Let S mole per liter be the solubility of the salt. Then numerically AXBY gives us X times AY positive plus Y times Bx negative. The solubility of the first ion will be X times S, and similarly the solubility of the second ion will be Y times S. So we will have the solubility product Ks is equal to the concentration of X times S raised to power X into Y times S raised to power Y. Together we have a cumulative multiplication equal to X times X into Y times Y multiplied by solubility raised to power X plus Y. For example, take the salt of type AB3. there are various salts of the type AB3. For example, we have aluminum iodide Ali3, ferric hydroxide FeOH whole thrice, chromium trihydroxide CrOH whole thrice, aluminum hydroxide AlOH whole thrice, etc. All of these salts are of the type AB3. They are called quaternary electrolytes because they produce 3 ions upon dissolution. Numerically, we can show AB3 gives A 3 positive plus thrice B negative. The solubility of A is S and the solubility of B will be 3 times S because there are 3 ions present in the solution. Let S mole per liter be the solubility of AB3. We will have the solubility product Ks is equal to A 3 positive multiplied by B negative raised power 3. So in terms of solubility, we have S into 3S raised power 3, that's equal to 27S raised power 4. Or we can have solubility is equal to 4 times square root of Ks divided by 27. Thus we derive a relationship between solubility and the solubility product for an electrolyte of the type AB3. We can derive equations for any other type of electrolyte of the type AB, AB2, AB4, etc., etc. Now friends, let us discuss Oswalds dilution law, which is very important for the present discussion. Consider a binary electrolyte AB which dissociates into A positive and B negative ions, and the equilibrium state is represented by the equation AB is in equilibrium with A positive plus B negative. Initially, at a time t equal to 0, we will have the concentration of AB equal to C, the concentration of A positive equal to 0, and the concentration of B negative equal to 0. After a certain time t, at equilibrium, the concentrations will change because AB will get converted to A positive and B negative. That time, we will have the concentrations of AB equal to C multiplied by 1 minus alpha, where alpha is the degree of dissociation of the electrolyte AB. And the concentration of A positive will be C alpha. Similarly, the concentration of B negative will also be C alpha. So, dissociation constant may be given as K is equal to concentration of A positive into concentration of B negative divided by the concentration of AB, which is equal to C alpha multiplied by C alpha divided by C multiplied by 1 minus alpha. That simply gives us an equation K is equal to C alpha square divided by 1 minus alpha. From the equation, it is clear that degree of ionization increases on dilution. Thus, degree of dissociation of a weak electrolyte is proportional to the square root of dilution. This law is called Oswalds dilution law. Oswalds dilution law is not applicable for every electrolyte and every electrolytic solution. We have limitations of Oswalds dilution law. The law holds good only for weak electrolytes and fails completely in the case of strong electrolytes. The value of alpha is determined by conductivity measurements by applying the formula conductivity at concentration C divided by conductivity at infinite dilution is equal to the degree of dissociation. The value of alpha determined at various dilutions of an electrolyte when substituted in the aforementioned equation gives a constant value of K only in the case of weak electrolytes like acetic acid, ammonium hydroxide, etc. The cause of failure of Oswalds dilution law in the case of strong electrolytes is due to the reason that the law is based on the fact that only a proportion of the electrolyte is dissociated into ions at ordinary dilution and completely at infinite dilution. However, strong electrolytes are almost completely ionized at all dilutions, and the ratio of conductivity at concentration C to that of conductivity at infinite dilution does not give accurate value of alpha. When concentration of the ions is very high, the presence of charges on the ions appreciably affects the equilibrium. Hence, law of mass action, its simple form, cannot be strictly applied in the case of strong electrolytes. That's all we have for you in today's lecture. Dear friends, hope you have understood it well. Thank you and goodbye.